The distant and perplexing world of Pluto was once considered a unique, legitimate planet within our solar system. However, after recent discussions by leading astrophysicists Neil deGrasse Tyson and Michio Kaku, Pluto has found itself once again in the spotlight, drawing attention due to their groundbreaking suggestions. These experts have proposed that Pluto may be on a potential collision course with Neptune. This idea raises numerous questions. How could such an event occur, and what might be the consequences of such a monumental impact? Are we witnessing a captivating cosmic anomaly, or is there a deeper, more complex phenomenon at play? Join us as we explore the possible implications of a Pluto-Neptune collision. Pluto, a former planet, which was once considered a smaller and more isolated member of the solar system, continues to be a topic of significant interest and investigation in the scientific community. According to prominent studies by leading experts, Pluto's orbit is dangerously close to Neptune's, and some astrophysicists, including Neil deGrasse Tyson and Michio Kaku, have raised alarms about a potential catastrophic collision between the two. Could such an event pose a significant risk to Earth? How could this happen? Pluto's orbit around the Sun is unlike that of any other planet in our solar system. It takes an extraordinary 248 years to complete just one full orbit. This means that since its discovery in 1930, Pluto has not yet even finished one entire orbit. However, the fascination does not end there. Pluto's orbit is shaped in an unusual, elongated pattern, differing vastly from the nearly circular orbits of the major planets. What makes Pluto's orbit even more perplexing is its tilt of 17 degrees relative to the ecliptic plane, making it one of the most inclined orbits in the solar system. This inclination, along with its irregular shape, adds to the complexity of its path through space. One of the most intriguing aspects of Pluto's orbit is how it intersects with Neptune's orbit. For about 20 years in each orbit, Pluto actually travels closer to the Sun than Neptune, defying expectations based on the relative positions of the two planets. This brings up the obvious question: why hasn't Pluto collided with Neptune? The answer lies in the gravitational influence of other planets. The study of Pluto's orbit began shortly after its discovery, with astronomers initially struggling to make sense of its unusual path. Unlike other planets, whose orbits lie relatively close to the ecliptic plane, Pluto's orbit stood out due to its extreme tilt and eccentric shape. The mystery behind the fact that Pluto's orbit crosses Neptune's is rooted in the stability of its path. The key to this stability lies in a phenomenon known as the three-body problem, which deals with understanding how three celestial bodies like Pluto, Neptune, and the Sun interact and influence one another's motion via gravitational forces. This problem is akin to trying to predict the future locations of these objects based on where they start and how they pull on each other. In Pluto's case, this problem shows how its orbit, Neptune's orbit, and the Sun's gravity work together in an intricate and balanced way. Terms like asymmetric libration, degree libration, and VZK wobbling are part of this complex issue. According to astrophysicists, what keeps all planets in their orbits is a form of libration. In the case of Pluto and Neptune, this term suggests that whenever Pluto crosses Neptune's orbit, it is always at least 90 degrees away from Neptune's position, which prevents a direct collision. Degree libration, on the other hand, refers to the oscillation of a celestial body in its orbit. For Pluto, this means that when it comes closest to Neptune, it is positioned far above or below Neptune's orbital plane, which further adds a layer of protection from potential collisions. Another critical factor in this stability is the VZK wobbling, named after the scientists who studied the way celestial objects move in space. This phenomenon explains how Pluto, Neptune, and the Sun affect each other's motions through their gravitational pull. The wobbling helps us understand why Pluto's path is so irregular. Despite its seemingly erratic movement, the forces at play work to keep Pluto's orbit stable over long periods. These forces are essential in maintaining the stability of Pluto's orbit, preventing it from crashing into Neptune or straying off course. The three-body problem and the dynamics of these gravitational interactions are crucial to understanding how orbits change over time and how celestial bodies affect one another. By studying these interactions, we gain insights into Pluto, our solar system, and distant stars and planets. Numerical simulations in the late 1980s revealed that despite these stabilizing factors, Pluto's orbit can be highly erratic, with slight changes in initial conditions leading to substantial differences over long periods. However, these irregularities have been shown to maintain a consistent orbit over vast stretches of time. Recent computer simulations have further helped scientists understand how the giant planets like Neptune, Jupiter, and Saturn influence Pluto's orbit. For instance, Neptune has a unique resonance with Pluto, where for every 2 orbits Pluto completes, Neptune completes 3. This resonance helps maintain Pluto's orbital stability. But Neptune is not the only force at play. Jupiter's gravity also plays a significant role in safeguarding Pluto's orbit. Saturn contributes to this protection as well. These simulations suggest that Jupiter's gravity alone is powerful enough to ensure that Pluto remains on a stable path for billions of years, possibly even indefinitely. The cooperation between Neptune, Jupiter, and Saturn appears to be crucial in ensuring that Pluto can continue to travel safely through space without encountering any major disturbances. These findings are important in understanding the broader dynamics of the universe. Without these stabilizing forces, the solar system would be a much more chaotic and unstable place. Objects like Pluto could potentially collide with other bodies or be ejected from their orbits, causing a cascade of disturbances across the solar system. For Pluto, understanding its orbit is particularly crucial in light of discussions about a potential future collision with Neptune. This gives us a clearer view of the dynamic nature of our solar system. The case of Pluto illustrates how even seemingly unstable orbits can achieve a state of balance through the intricate interactions of gravitational forces and orbital mechanics. It also highlights the importance of continuous research and analysis to better understand our place in the universe. Exploring the depths of space often forces us to confront the unpredictable nature of celestial bodies, and Pluto's orbit serves as an ideal example of this unpredictability. The concept of orbital resonance, which refers to the delicate balance of a celestial body's orbit based on its initial conditions, is clearly demonstrated by Pluto. This means that even slight variations in Pluto's position or speed can significantly alter its long-term orbital path. Programmatic simulations have been invaluable in studying how Pluto moves through space. These simulations use complex mathematics to model the gravitational interactions between Pluto and other celestial bodies, such as Neptune. By altering small details in these models, astronomers can observe how tiny changes can lead to dramatic shifts in Pluto's future position. These simulations revealed an interesting fact about Pluto's orbit. Despite the stabilizing mechanisms like asymmetric libration and degree libration, its orbit can still be highly erratic. Even the smallest changes in Pluto's starting position or velocity can cause its orbit to evolve in unpredictable ways over long periods. Nonetheless, despite this chaos, Pluto's orbit remains remarkably stable over billions of years. This suggests that there is an underlying order to Pluto's journey around the Sun, even though it may appear chaotic at first glance, especially when considering the complexities of Pluto's highly inclined orbit. The unpredictability of large orbits like Pluto's presents significant challenges for astronomers. The inherent nature of these systems suggests that long-term predictions are often fraught with uncertainty. While numerical simulations are an excellent tool for understanding and predicting the future behavior of celestial bodies, they also underscore the limitations of our predictions. These models heavily rely on the accuracy of initial conditions and the complexity of the interactions they simulate. A slight error in these conditions can drastically alter the predicted outcome, making precise predictions an incredibly difficult task. Furthermore, the tumultuous nature of large orbits like Pluto's serves as a reminder of the constantly evolving and dynamic nature of the universe. Although we have made significant strides in understanding space, Pluto's example reminds us how much more there is to learn. Understanding the gravitational effects of the giant planets on Pluto's orbit provides valuable insights into the broader dynamics of our solar system. It illustrates how the positions and motions of individual planets can have far-reaching consequences for the stability and trajectory of other objects in the system. But why are prominent astrophysicists now raising concerns about a potential collision between Pluto and Neptune, despite all these complex forces at work to prevent such an event? Neil deGrasse Tyson, a renowned astrophysicist, offers a detailed perspective on the mysteries of our solar system, particularly through the fascinating example of Pluto. Tyson, who played a significant role in reclassifying Pluto from a planet to a dwarf planet, provides an insightful analysis of the evolving nature of celestial mechanics and the public's growing interest in the overlooked corners of space. The reclassification of Pluto, Tyson argues, was not a diminishment but rather a necessary adjustment in light of our expanding knowledge of the many bodies that orbit our Sun. Tyson's approach to celestial mechanics is one of continuous learning and adaptation. He views the complexities of Pluto's orbit and its interactions with Neptune as a reminder of the unpredictability of space. While he acknowledges that Pluto's orbit is stable for now, he suggests that it could undergo significant changes in the future. This possibility highlights how much there is still to discover about the forces that shape our nearby solar system.